Hello viewers, welcome back to my channel. Today I am here with a new video on simple harmonic motion and oscillation under MAKAUT B Physics syllabus paper code PH101 or 201. Before that, আপনারা এখনো যদি এই চ্যানেলটি সাবস্ক্রাইব না করে থাকেন তাহলে সাবস্ক্রাইব করে দেবেন এবং বেল আইকনটি প্রেস করবেন। If you have not still subscribed this channel, please do subscribe the channel and press the bell icon. আমার ভিডিওগুলি যদি আপনাদের ভালো লেগে থাকে তাহলে অবশ্যই লাইক করে দেবেন এবং অন্যদের সাথে শেয়ার করে দেবেন। And if you want to join my online classes, আপনারা যদি আমার অনলাইন ক্লাস জয়েন করতে চান, you can contact me through WhatsApp, Instagram and Facebook direct message. All these are given in the background of my screen. So let us start the class. So in my previous class, I have already discussed about different types of damped vibration and their significances. Now I will discuss some extended terms and topics of damped harmonic vibration. First of all, I will discuss about relaxation time. First one is called relaxation time in damped oscillation. So there is another way of expressing the damping effect of damped harmonic oscillation or damped harmonic vibration, and this is done in terms of time. So the time in which the amplitude of the damped vibration or damped harmonic oscillation reduces or decays to 1 by e of its initial amplitude, that is called the relaxation time. So the time required to decay the amplitude of a damped harmonic oscillator to 1 by e times of its initial amplitude is called the relaxation time. Suppose that time is denoted by tau. Suppose tau is relaxation time. Now we know the expression for displacement of a damped harmonic oscillator is given by this equation. So here we know that this displacement has an amplitude part and that depends on exponential term. Here all the symbols have their usual meaning that I have already discussed in my previous lecture. Now the amplitude part is, suppose, some constant c into this exponential term. Here the constants are, for this coefficient constant is this one, second term constant is this one. So in general we take the amplitude is, suppose, constant c into e to the power of minus a into t. This is the amplitude part. So according to the condition of relaxation time, the amplitude after a time interval of tau or relaxation time tau, amplitude would be c e to the power of minus a t plus tau, and that amplitude would be, according to the definition of relaxation time, 1 by e times initial amplitude, that is c e to the power minus a t. Or from here we get e to the power of minus a tau, that is equals to e to the power minus 1, or a tau equals to 1, or tau equals to 1 by a. Which is the expression for relaxation time. Where 2a equals to b by m or a equals to b by 2m. All these symbols and their meanings have been discussed in my previous lecture of simple harmonic motion and oscillation. You can go there and watch the video for details. Still I am telling again, that is b equals to, b is called resisting force per unit velocity, or which is also called the damping coefficient, and a is equals to b by 2m. So the relaxation time is inversely proportional to a, this tau equals to 1 by a. Next, another significant term in damped harmonic oscillation is called the logarithmic decrement, and also it came as a question in MAKAUT 2013 and 2020 as a 4 marks question about logarithmic decrement and relation between logarithmic decrement and relaxation time. So let us discuss the logarithmic decrement in damped vibration. So the general solution for displacement of a damped harmonic oscillation is given by equation 1. Now for underdamping case, this expression turns into equation 2. So displacement for underdamping case becomes oscillatory in nature, that is x equals to d to the power minus at cos of omega 1 t minus delta, where omega 1 is a square minus omega 0 square. All the terms has their usual meaning that you can find in my previous lecture. So here the amplitude part is this part, d to the power of minus of at. Amplitude part is d to the power of minus of at. So we will find out ratios of amplitude of two consecutive displacement maximum. That means, and suppose after the time period of tau 1 we will find two consecutive amplitude maximum for two different displacement maximum. So the ratios of the amplitudes of two displacement maximum would be d to the power minus of at divided by d to the power a t plus tau 1, where tau 1 is the time period. So it would be simply e to the power of a tau 1, and that ratio is denoted as decrement d, which is also called decrement, and that is equals to e to the power of a tau 1. If you take log both sides, then it would be logarithm of d, that would be equals to a tau 1, and this is called logarithmic decrement, and this ln d log d is called logarithmic decrement or log decrement. Previously we have found out that relaxation time is tau equals to 1 by a. Now we found logarithmic decrement, which is log d equals to a tau 1. Again relaxation time is tau equals to 1 by a. Now if we put it here, we will get log decrement equals to 1 by tau into tau 1, or logarithmic decrement equals to tau 1 by tau, where tau 1 is the time period of two consecutive displacement maximum amplitude and tau is the relaxation time. So this is the relation between logarithmic decrement and relaxation time in damped harmonic oscillator. Next we will prove that total mechanical energy is not conserved in case of underdamped vibration. Now for underdamping case, the expression for displacement is x equals to d to the power of minus at cos of omega 1 t minus delta, which we have already discussed in my previous lecture. Now here displacement term is this one. So from here we will get the velocity term x dot equals to dx dt, which is equals to d to the power of minus at into minus a cos of omega 1 t minus delta minus of d to the power of minus at into omega 1 sine of omega 1 t minus delta. So we get two terms for the velocity part. Now to calculate the total energy, we have to first calculate the potential energy, which is given by half k x square, which is half k into d square e to the power of minus at 2at cos square of omega 1 t minus delta. So this is the expression for potential energy, and similarly for kinetic energy we will get half m x dot square, and we have to put the value of x dot here. So we will get half m into, we have to put the expression for x dot square. So total energy would be kinetic energy plus potential energy. So this is the potential energy part and this one is the kinetic energy part. So in both cases we can see that potential energy and kinetic energy both depends on this exponential term, that is e to the power of minus at term. So the total energy will also depend on e to the power of minus at term, that exponential term. So the total energy also varies with e to the power of minus at term. So the total energy would be given up to the damping medium, and also the energy would be dissipated through heat. So the total energy for underdamped vibration would not be conserved. It would be dissipated through heat and it would be given up to the damping medium. If we plot the energy, total energy versus time for underdamped vibration, the graph would be like this. So this is the graph for total energy versus time graph for underdamped vibration or underdamped oscillation. Now we will calculate the energy loss rate in case of under damped vibration. For that, we will start with equation of motion. So the equation of motion of the damped vibration is given by this one. Equation 1, m d2x dt2 equals to minus b dx dt minus kx. Here the retarding or resisting force is this term, that is b minus of b into dx dt. So that retarding and resisting force depends on velocity dx by dt or x dot. So it depends on velocity. Now the instantaneous loss of energy P, that is equals to minus of d dt, that is equals to retarding force into instantaneous velocity. So retarding force equals to minus of bx dot into again instantaneous velocity is x dot. So the instantaneous loss of energy P, which is equals to minus d dt, that is equals to minus of bx dot square. So it depends on velocity square. So when velocity is maximum, this loss, instantaneous loss of energy, is also maximum. And the velocity, when velocity x dot is 0, then P becomes 0. So the energy loss rate in case of under damped vibration depends on the instantaneous velocity. When the instantaneous velocity is maximum, the loss is maximum, and similarly when instantaneous velocity is 0, the loss is 0. So the energy loss versus time graph for under damped vibration would be this figure. So this is the graph for energy loss versus time in case of under damped condition or under damped vibration. So along y-axis, negative y-axis, d minus d dt would be plotted, and along positive x-axis time. So this figure denotes the energy loss versus time graph for under damped vibration. So this is the end of this today's video. See you in the next video or next class. Till then, bye.
Like and share it, and don't forget to subscribe the channel.